Okay, I'm back. Part 3, here we go. Alright. So we got a whole mess of piecewise functions and we're trying to do the same thing we always do, which is analyze the function for continuity, or a lack thereof. So look here. You got a negative 2, and a negative 2, and a negative 2. Then you got a 4, and a 4. So those would seem to be the two places that I would be most concerned about. But we do have three whole functions. We've got the orange guy here. We've got the lavender guy here. We've got the blue guy here. We've even got red, orange, yellow. I don't like yellow. Green, blue, violet. I like gray better than I like yellow. So we've got a gray function. All right. So what's the deal? Looking at that orange guy, is he continuous everywhere? The answer is yes, because he's a polynomial. So I can rest assured that from negative infinity right up to negative 2, yes, I am continuous. This lavender guy, he's just a number, and he's not really defining a whole interval. He's just giving us a single function value at negative 2, so that's not really helpful. But in blue, I have a radical, and luckily for me, x squared plus 2 is never ever negative. So this actually would have a domain that goes from negative infinity to infinity and has no discontinuities. So that blue guy does tell me that I'm continuous from negative 2 all the way to 4. And ln of x, I know you guys don't know a hell of a lot about ln, but ln is just like any other log. So I do know that it has a vertical asymptote at 0. And because its base is e, meaning 2.7, which is greater than 1, the graph would increase quickly up that asymptote and then level off. So no, it's not continuous from negative infinity all the way to infinity, but it is continuous on its entire domain, which goes from 0 to infinity. And we're only concerned with what's happening from 4 to infinity anyway. So certainly from 4 to infinity, we can say that yes, we are continuous. So that covers a hell of a lot of area. We're continuous on all this stuff. So again, we do see that the only potential problem spots are negative 2 and 4. And for negative 2, we have three functions to check. We have the left-hand limit, the right-hand limit, and then we have the actual function value. So just like before, my left-hand limit is when I'm less than negative 2, so that's going to come from the orange function. So I'm going to go ahead and switch over, be a little less formal. But let's go ahead and say that when x is negative 2, your left-hand limit is going to be given by this expression. It'll be negative 2 cubed minus 3 times negative 2, which is negative 8 plus 6, which is negative 2. Yeah. Huh, okay. Then what else do I know? I know that from the purple guy, that's just literally telling me that f of negative 2 is 3. So okay, great. Right away I can say that we're definitely not continuous because one of my limits is different from my function value. But to fully answer the question of what's going on, we still need our right-hand limit, which is going to come from the blue function here. So the right-hand limit, that's going to be given by the opposite of the square root of a negative 2 that is getting squared plus an extra 2. So that's going to be the opposite of the square root of 4 plus 2, which is 6. So it's negative root 6. So all three of these values are different. And what that means is we have a jump discontinuity. It also means that I don't really care about the function value. He doesn't do anything. All that matters is the fact that these two limits are different. I now know that for sure there's a jump discontinuity at negative 2. And I can now take all that stuff. Let me lock this. Lock. Then I can grab all this. Yep. Grab all that, shrink it down. And now we have to start a second look at what's going on at 4. And 4 only cares about the blue function and the gray function. So the limit as we approach 4 from the left will come from the blue. So for x equals 4, my left-hand limit is going to come from the blue expression. Oh, geez. And it's going to be the opposite of the square root of a 4 that's getting squared plus an extra 2. That's the opposite of 16 plus 2, which is 18. So it's negative square root of 18. Now your right-hand limit is going to be for the x is greater than 4. That'll come from the gray expression. So that'll just be, oopsies, the right-hand limit will literally just be the ln of 4. And what's the ln of 4? I don't know. I don't know what it is. But I know it's not the same thing as the square root of 18. It just isn't. Okay? So we have the exact same conclusion to make here, is that at 4 we are getting another jump discontinuity. And because it's a jump, I don't actually care what the value of the function is, but for those of you who are curious, 4 is, we're allowed to be 4 here in this third interval. So the actual function value, if I asked you what is actually f of 4, f of 4 would come from the same blue expression. It would give us the same negative root 18. But again, we don't care. For the jump discontinuity, all you would ever have to show is that the two limits, the left and right hand limits, are different. So for this guy, it says identify the type of each discontinuity and where they're located. You would tell me that when x is negative 2, we're getting a jump discontinuity, and you'd include the limits to justify that answer. You'd say that x equals 4, we're getting another jump discontinuity, and you'd include the limits to justify that, and that is number 5. Let's do number 6 the same way, including the same color coding. We've got a linear function in orange. In lavender, we've got another constant. In blue, we've got a quadratic. And in gray, we have another constant. So how's this one go? I'm certainly concerned about what's happening at negative 1. So let's say when x is negative 1, yoink, I'm going to get a left-hand limit, meaning I'm sneaking up on negative 1 from the left-hand side where things are less. That's going to come from the orange. So it'll be 2 times negative 1 plus 1. That's negative 2 plus 1, so negative 1. That's my left-hand limit. My right-hand limit will be for the x's that are bigger than negative 1. That's going to come from the blue. So your right-hand limit is going to be negative 1 squared minus 6 times negative 1 minus 6. So negative 1 squared is positive 1, but then there's another negative to turn us back into negative 1. Then we're adding 6. Then we're taking away 6. Adding 6, taking away 6 cancels, you get negative 1, which has me starting to think, hey, maybe we're continuous, but no, we're not. Because in lavender, f of negative 1 is defined to be 3. Okay, so what do you call it when your limits are the same but your function value is something else? That's a removable or a point discontinuity. Exclamation point. So that's it. I've got my limits. I've got my justification. I know that I'm getting a point discontinuity here at negative 1. Now I'm wondering what's going on at positive 1. And of course, I can go ahead and start doing this. I would start by finding my limit from the left, which will come from the blue expression. So my left-hand limit equals the opposite of 1 squared minus 6 times 1 minus 6. So I'm getting another negative 1. Take away 6, take away 6. That is negative 13. Okay, then my right-hand limit comes from, well, it's 3. All right. So I seem to remember a time when we talked about what kind of discontinuity you have when your left and right hand limits are different, because it happened over here twice. It was a jump and a jump. So this is a jump. And that's it. So can we safely say that we're continuous everywhere else? Yes, because lines are continuous. Parabolas are continuous. So if you had to say where we are continuous, you know that it would be from negative infinity right up to the first discontinuity at negative 1. Then we're fine from negative 1 to 1. Then we're fine from 1 to infinity. So here's the 3 intervals on which we are continuous, and here's our 2 discontinuities classified using limits. I'm so close to the end, I may as well finish, right? All right, so here goes. Sure, let's do it again. I'll even keep on color coding. In rows, you've got an exponential expression. In orange, you got a constant. In green, that's actually a rational function, kind of just a simple rational function. And in blue, you got another line. All right, again, to the left of -2, are we good? Are we continuous? The answer is yes, because the graph of 2 to the x, exponentials, if you remember, they have horizontal asymptotes at 0. Then when the base is greater than 1, like this one is, you're kind of flat at first, and then you really quickly take off and grow, grow, grow. So looking at this, to the left of -2, yeah, we're good. There's no breaks anywhere on an exponential. So to the left of -2, there's no breaks. So I am ready to safely say that we're definitely continuous from -infinity up to -2. Okay, this again is just a single point. That doesn't help me with my continuity. Now 1 minus 1 over x squared, that's just a rational function. And I can see that it's giving a vertical asymptote at 0 because the 0 of the denominator is 0. And I know that because we're bottom heavy, the horizontal asymptote, well, it would have been at 0. But this 1 over here, if I kind of reverse the order of the terms, that's like a +1 on the end. That wants to shift us up by 1. So you'd have a horizontal asymptote at 1. But this asymptote that's at 0, look at where we're being defined. We're only being defined from -2 to -1. And within that window, I'm just going to see a little chunk of hyperbola doing its thing, right? Because the only discontinuity this function has is at 0, and I did not give you an interval that included 0. So all this lovely discussion I just gave you, maybe it had no real point, because I am again ready to say that function should be continuous between -2 and -1 because its only discontinuity is at 0. So yoink, -2, -1. We're good. Then the next guy is a line, and lines of course are continuous all the way from -infinity to infinity. So I can definitely say that I'm continuous from -1 to infinity. Okay, great, I did it. These are the intervals on which I'm continuous. Unless, what if I'm continuous at -2? Maybe I am. What if I'm continuous at -1? Maybe I am. Let's go test that. So if we let x equal -2, then we're going to do that test by finding the left-hand limit, the value of the function, and the right-hand limit. We do this every stinking time. So who's giving me the left-hand limit? I bet it's this guy to the left. It's going to be the red guy. So I'm doing 2 to the -2. When you have a negative exponent, that asks you to take the reciprocal of the denominator. So 2 become the reciprocal of the base, my bad. So that means we're now just doing 1/2 to the power of 2. That gives 1/4. So your left-hand limit is 1/4. The value of the function, oh, would you look at that? It's 1/4. So I'm starting to think maybe, just maybe, we're continuous. Comes down to the right-hand limit. The right-hand limit is going to be given by this green guy, which is 1 minus 1 over -2 squared, which is 1 minus 1 over 4. But 1 is 4/4, and 4/4 take away 1/4 is 3/4. So that spoils it. We are not continuous because it would only be continuous if all three of these were the same. So taking a closer look, I see a left-hand limit that's 1/4 and a right-hand limit that is 3/4. So they're very close to each other, but they're not the same. They're different. So this is another jump discontinuity. Okay. I think I'm back. Yeah, I stepped away for a minute. Where the heck was I? Looks like we were testing the -2, and it was a jump discontinuity. Um, so the next one. Oops. Okay, great. So we're going to test at -1 now, see if we're continuous or if we have some kind of discontinuity. And again, to test at -1, we are going to have to... -1? Yeah, -1. So we're going to have to find the right hand limit, left hand limit, yada, yada, yada. So left hand limit, function value, right hand limit. Okay, where's the left hand limit coming from? It's going to come from the green. So that's going to be 1 minus 1 over -1 squared. So that's 1 minus 1 over 1, which is 1, which is 0. The function value is going to come from the blue expression. So that'll be 5 times -1 minus 1 negative 5 minus 1 is -6. And then the right hand limit is the same. It's going to come from the same blue expression. So it'll also be -6. But again, I'm noticing that my limits, that's the 0 and the -6, they are different. So this is another jump discontinuity. This worksheet apparently loves the jump discontinuity. A lot of those. But that's it. So since both of these are jumps, these would be our intervals. I don't have to put any of the intervals together. So we get the red, the green, the blue. Those are the intervals on which we are continuous, and we're getting jump discontinuities everywhere else. Let's do 8. Shrink. Move. All right, so for 8, I really got to do this? I'm not getting repetitious? You guys still watching? Pink and orange, green and blue. All right, again, any special discontinuities anywhere? Nope, because this is quadratic. So we are continuous from -infinity to 1. Then the orange isn't doing anything. That's just a point again. Logs are continuous. We talked about this already, I think. The log base, or the log base E, or ln, has a vertical asymptote at 0, and then it goes. But again, we're going from 1 to E. So 1 would put us like here. E is like 2-ish, so it's here. So we're definitely talking about just a little bit of this function, and on that little bit we are continuous. So from 1 to E, we're good. And then 4x is another line, so from E to infinity, we're good. So I know for a fact that we're continuous on those intervals, and I'm just worried now about what's happening at x equals 1 and what's happening at x equals E. So what's happening at 1? Well, as usual, we're going to test our left hand limit and our right hand limit and the value of the function. And the left-hand limit will come from the pink function, this quadratic, and 1 minus 1 squared is 0. For the right-hand limit, that'll come from the green. We're approaching 1 from this side. So that's the ln of 1, which I hope you remember is 0. Log base anything of 1 is 0. So far, this is looking like a point discontinuity, but it might be that we're continuous, but it isn't, because right at 1 we're getting -2. So the function value is different. So that means I can conclude that at x equals 1 we're getting a point discontinuity, or a removable discontinuity. Okay, so what's happening at E? Well, we're going to test the same things. We're going to test our left hand limit, our right hand limit, and the function value, which will be f of E. So what's the left hand limit? It's going to come from the green. And that'll be the ln of e, which is 1. Forgive me, that should be green. The right-hand limit will come from the blue. So that'll be 4e, which again, I don't know what that is, but I know it's different from 1. And what's f of e? F of e is coming from the green again. So that'll be the ln of e again, which is 1. But again, I'm getting two limits that are different. So this will be another jump discontinuity. So we're not seeing a lot of vertical asymptotes here, but notice we could have had I'm sorry, we're not, oh yeah, no, I said that right. We're not seeing vertical asymptotes, so we're not seeing infinite discontinuities, but if you're curious, I could have let this be 0, and this be 0, and this be 0. And if we did that, then suddenly the limit as we approach to 0 would be given by the log, and we would go to negative infinity. And if we had made that change, then we could get an infinite discontinuity from our piecewise function, because the log function naturally wants to give us a vertical asymptote. And what else would happen? We'd be getting an actual point at -2 from the orange. The pink would be giving us an upside down parabola. So it would have us at 0 would be up at 1, open, and just kind of coming down like this. And then of course the 4x, I don't know, would have us somewhere weird, would be like up here or something going barrel. But you'd be looking at a graph that's something like this. And we can see that here my left-hand limit would be 1, it would be a finite value, but my right-hand limit would be going to infinity. So we could get an infinite discontinuity. I want to mention that because we're not really seeing it on the worksheet. But you might see it on the quiz. So moving on. So these are back to the solve for k to make us continuous thing. And again, if you want to be continuous, then you know that what you need is for the left-hand limit to be equal to the function to be equal to the right-hand limit. And we're trying to be continuous at 4 because we know we're continuous everywhere else. It's just the 4 that we're worried about. So the left-hand limit would come from the 3 minus x squared. So that'll be 3 minus 4 squared. The value of the function would come from there too. It would literally just be 3 minus 4 squared again. So obviously those are equal. And then the right-hand limit would come from the x plus k, which will be 4 plus k for us. So basically for all of these things to be the same, we get 3 minus 16, that's negative 13. This of course is negative 13. And so for 4 plus k to be negative 13, we'll just subtract 4 from both sides, we'll get negative 17. And we see that if we let k be negative 17, then we will end up continuous, because the left-hand limit will be negative 13 and the right-hand limit will be also. So that would be our value of k. And for 10, I mean, we're doing the same thing. We still just want left-hand limit to equal right-hand limit and to be the same as the value of the function, so at -1. Right or left-hand limit will come again from here, so x squared plus k, meaning -1 squared plus k. The right-hand limit would come from this guy, so 5 times -1 minus 2. And of course the value of the function is going to come from the same thing that the left-hand limit came from, the top expression. So I don't even need to include that really. We already know that the left-hand limit and the function value are the same. So I can just worry about these two parts. And I'm getting a 1 plus a k that needs to equal a -5, take away 2, so -7, take away 1 more. That tells me that as long as I let k be -8, we'll be continuous at -1. So that's it. It is late, so I think I said that I'd go back and do more, but I just don't think it's worth it. I don't think there's anything there to talk about that we haven't talked about already. Not really. We did the algebra of these. You guys know to use the conjugate to simplify that. We talked about factoring for sure a whole bunch. Oh, this is maybe worth mentioning again. So if you're still tuned in, limits as we go towards infinity, of course, those are more based on the horizontal asymptote. So you could get away with finding the limit as we go to infinity pretty easily by just thinking about the horizontal asymptote. And if you remember the rule, when the denominator has the greater degree, you know your asymptote's at 0. So if I'm not telling you to justify or show any work, you know this limit is going to go towards 0 because that's where the horizontal asymptote is. If I was saying that you had to show some work, then the way that we get this to go is we multiply by 1 over the greatest power of x among all the x's, so an x cubed. And you'll do that in the numerator, and you'll do it in the denominator. And you'll do that because when you do it, all of these terms will turn into little rational terms. We'll get 3x squared over x cubed, and the x squared will cancel with the x cubed to give you a 3 over x. You get a little fraction now out of every single term. And all of those fractions that have x's in the denominator, they all go to 0 when you sort of imagine going toward infinity. As the bottom gets big, 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 the whole fraction gets small, 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 small as it goes towards 0. So next you would have a 2 over an x that is squared. That still goes to 0 when you imagine infinity. And then you get a 7 over x cubed. That goes to 0. In the denominator, you get 2x cubed over x cubed. So that's the one term that the x's cancel, and you don't have x's in your denominator anymore. So now that limit, the limit of a constant, is the constant. That'll be 2. Then you get minus x over x, which is 1 over x squared. So by breaking it down like that, we can now use the property of limits that says it's fine to just take all these limits individually. So in the numerator, you get a limit that goes to 0, another one that goes to 0, another one that goes to 0, then you get a 2 minus 1 that goes to 0. So that's 0 over 2. That's not the indeterminate form. That's not 0 over 0. It's 0 over 2. So that is just 0, telling us that the answer was 0. So don't forget that little thing there. We talked about that a bunch. E is another one. Again, if you don't have to show any work, then you can look at this and notice that you've got an x cubed and an x cubed. That means the powers are equal, and that means your horizontal asymptote will be at whatever fraction you get when you just do the leading coefficient divided by the leading coefficient. So I expect I expect this guy's horizontal asymptote to be at negative 2/5. So it would be like here, just barely below the x-axis. But that tells me my limit is negative 2/5, because the limit as you go to infinity is equal to the horizontal asymptote. Again, if you did have to show work, then we would again just divide everybody by the highest power of x, and we would turn this into the limit as x goes to infinity of x over x cubed is 1 over x squared, and then 3 over x to the 1 minus 2, because the x cubes cancel. So I get a constant there. Then here, the x cubes cancel, I get 5. Then one of the x's cancels, but I get a 4 over an x squared. And then this is 7x cubed. And so now that I've rewritten my expression like this, I can again just do the limit of this, 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 and I can get my limit that way. So all of these terms with x's in the denominator have limits that go to 0, 0. But the constant, the limit is the constant. And at 5, your limit would be 5. But these guys go to 0 and go to 0. And then lo and behold, your limit is a negative 2 over a positive 5, which is negative 2/5. So the algebra for finding this limit, it's not that hard. But you should also have a graphical approach that says that this limit is nothing more than the horizontal asymptote of the function, which is negative 2/5. I said, don't worry about that function. Okay, so this guy here, again, if I'm expecting you to show work, then what do? You can't plug in 3 technically because you'd get 5 over 3 minus 3, which is 5 over 0. But hopefully by now you know that what this is not the indeterminate form. This is just us being undefined. And us being undefined implies a vertical asymptote, which implies a limit of infinity. But depending on how the graph goes at 1, 2, 3, does the graph go up the asymptote on both sides? If it did, then your left and right hand limits would agree and your limit would be infinity. But more often than not, you're going to have the graph going up the asymptote on one side but down the asymptote on the other side. Then your left and right hand limits don't agree, and you would say that this limit does not exist. You'd have to do something. If I was actually asking you to sort of justify this answer, you better do something. Draw me this picture. By the way, is that picture right? Let's see. If I'm less than 3, then less than 3 minus 3 would be negative. So no, this picture isn't right, because it would be going down on the left and up on the right. So your left hand limit would be negative infinity, your right hand limit would be positive infinity, and that would justify saying that the limit does not exist. I think I'm good. I don't think I'm doing any more, because I talked about all these. Alright, I hope these videos were helpful. I know they're coming pretty late, especially this one now, but I hope they were helpful. Again, if they were helpful, at least say that to me. Give me some kind of feedback that this was worth my time, because this took me 3 hours. Just saying, 3 hours. Okay, bye.